Welcome to Chapter 3, Numerically Summarizing Data. Now that we have displayed our data and we know how to make a variety of visuals, we're going to move on to doing our numerical summaries. And coming out of Chapter 2, once we have data, we know we can make a visual display, like a histogram. And we've been interested, or we are going to be interested in three things. First of all, we know that we can look at the shape of a histogram, and we use words like bell shape, skewed left, skewed right, uniform. All right, so we can look at the shape from a histogram. We are going to talk about the central tendency, or the center of our data. So those are words like averages that we've used before, median, mean, stuff like that. That's what we're doing in section 3.1. And then finally, we also describe the data's spread. So is the data close together? Is it spread out really far? Stuff like that. And that's going to be section 3.2. Okay, so first off, when we talk about the central tendency, it's an average value of the observations, and we are going to look at three central tendencies in 3.1. We're going to look at the mean, which is what people normally think of when we say average. We're going to look at the median, and the one we don't use as often is the mode. All right, but it still measures central tendency. Okay, so the first is the mean, the arithmetic mean. So the definition is this: the arithmetic mean of a variable is computed by adding all the values of our variable in the data set and dividing by the number of observations. All right, so we can see just by this definition that this is definitely a numerical summary. So just in parentheses, just write ourselves a note. This is our first numerical summary. Okay, so we're going to look at the formula. We're going to look at the formula for our mean and for population and for sample. So first of all, we're talking about numerical summaries. Remember, a numerical summary for a population is called a parameter. So I'm going to write that to remind ourselves. And a numerical summary for sample is called a statistic. Okay, in addition, we have special notation, of course, right? This class is all about special notation. For population, we always use Greek letters. And then for samples, to notate samples, we use Roman letters like A, B, C, D, E, F, G, stuff like that. Okay, so a population mean, the population mean, we use a mu. Looks like a fancy U. So this will always mean or indicate the population mean. And it's pronounced mu. Mu. All right, and then over yonder, for a sample mean, we use lowercase x with a bar on its head. Let me write that a little bit better. A lowercase x with a bar on its head. And this always indicates the sample mean. And we say x bar. X bar. Okay, and so from our definition, we have to add up all the observations and then divide by the total amount of observations. So that's what it looks like as a formula. So here's our population. We have capital N observations, since capital N is our sample size. So we add up all the observations and then divide by the sample size. All right, and then likewise, little n is our sample size. So we add up all those little n observations and then divide by n. And then here we're introducing summation notation because this is a little clumsy of writing like that. It's a capital epsilon. It means to add up the x's 1 through n. So sometimes instead of writing a giant sum, we'll just write this capital epsilon, and that means the same thing. That's the definition of capital epsilon. So that right there, that's highlighted, we could rewrite it like that. So x1, x plus, or this shortcut way of writing it is using a capital epsilon. Summation notation is what we call it. Okay, so let's talk about what the mean represents. Physically, the mean is where the histogram is balanced. So I'm going to draw a curve instead of all of our histogram bars. So let's say we had, I'll draw 2 histograms. Let's say we had like a bell-shaped histogram, and then let's say we had a skewed right histogram, something like that. Okay, so we can imagine the bars instead of the curves. So if we were to balance something that's symmetrical, where does something symmetrical balance? Right down the middle. So the population mean is right in the middle of a bell-shaped curve. Let's look at over here. Most of the weight is right here. Remember, height means frequency, represents frequency. But with the skewed right, we have this value over here, and it holds a lot of weight because it's an extreme value. So while this is the majority of the weight, and maybe we would think that the mean would be somewhere right here, this extreme value is going to pull the mean in that direction. So really the mean is going to be balanced, or the histogram will be balanced right there. Okay, so just something to consider. Let's look at an example. We're going to find the mean. So the following data represents the monthly cell phone bill for 6 randomly selected months. There they are. We're going to compute, remember instructions are important, we're going to compute the mean phone bill. All right, so what our formula says is, well, is this a sample or a population? It's a sample because it's 6 randomly selected months. So we're going to use X bar for our notation. And we're going to add up all 6 of these values. So you can take out your calculator. And add them all up. Hit enter. After you hit enter, divide by 6. Oops, I have to write the last one up here. Sorry about that. And when you take that whole sum, if you're doing it in one line, put parentheses in the numerator for order of operations. Rounded, we might get something like 41.4067. And that answer will get you partial credit. Mean and central tendencies always have units. So where did that come from? Well, we are adding up 6 randomly selected phone bills. So this is money. So we need a dollar sign. And when we're talking about dollars, we normally round to the nearest penny. So our answer would be $41.41. So I would write this on a note card. Mean, median, mode, any central tendency needs units. And units is how we're measuring it. So in this case, the unit was dollars. We were measuring it in terms of dollars. All right, so that's a big one. So write that on your note card for the exam. All right, so next we have that the median, or the median is our next central tendency. I like to think of it as the physical medium. physical middle, like the median of a highway. So the median of a variable is a variable that lies in the middle of the data when arranged in ascending order. And we use capital M to represent the median. So again, median, think freeway. Okay. So let's find the physical middle. Here's some data that represents the flight time in minutes of a random sample of 7 flights from Las Vegas, Nevada to New York, New Jersey on Continental Airlines. We're going to compute the median flight time. All right, so there's our keyword. So we can do that in 2 steps, and I have those steps for you right here. The first step is to put the data in order, because that's the definition of the median. It's the middle of the data when arranged in ascending order. All right, so let's sort through this. Let's see, 257. That's the smallest value, and then we have 260, and then 260 again. We'll write it twice. 266, 267, 270, and then 282 comes next. Okay, so finding the physical middle, well, we can work our way out from the outside in. So we could put our fingers on the 2 extreme values, the smallest and the largest, and then move our fingers in 1, twice, till we get to the 1 value in the middle. So it looks like that 266 is the physical middle where we arrange the data in ascending order. So we could just say right now it's 266. And remember, mean any central tendency as units. And it's a flight time, we're measuring it in minutes. So minutes is the unit. 266 minutes. So there you go. If we had a large data set and we weren't able to just kind of look at it using our fingers, we also have a formula. For an odd amount of observations, the median is the m plus 1 over 2 observations. So let's do that for our example. What's our sample size? 7. So the median would be at 7 plus 1, which is 8. It would be the 4th observation. So let's go to our arranged data, and we can count. We can go, here's our 1st observation, 2nd, 3rd, and 4th. All right, so that's consistent. So we have 2 ways of doing it. Either we can just use our fingers and work our way from the out to the center, or we can have a formula too. Let's look at a different example. This time we have an even amount of observations. There's 6. And again, we're going to compute the median phone bill. Notice this time, let's look at this. Our first step is always to put the data in order. Oh, it's not in order. I thought they would be nice to us. All right, so let's put it in order. So the smallest value and then we look for the second largest, or the, second smallest, etc., etc. Almost done. Okay, so again, the median is the physical middle. We can do the same thing as before. Put our fingers on the smallest and largest and then walk them in one by one. And this time when we do that, we actually get 2 numbers in the middle, 39.43 and 42.09. All right, so what we have to do in that case is we have to find the number essentially between them, which is the same as the mean. So because it's even and we have 2 numbers in the middle, we have to find the mean of those 2 numbers. So calculator problem, I'm going to write it over here. So again, remember it's dollars. We can round to the nearest penny. Median needs units. We're looking at 40.76. So just as before, just in case there's a large data set, it's nice to have a formula. And let's look at these instructions. For an even amount of observation, the median is the mean of the n over 2 and the n over 2 plus 1 observation. So our n was 6. So 6 over 2 is 3. We have to look at the third observation. And 6 over 2 plus 1, or 3 plus 1, is 4. So we have to take the mean of the third and the fourth observation and look up here. When we put the data in ascending order, there's our first observation, our second, our third, and our fourth. And that's what we did. We took the mean of the third and the fourth observation. Okay, so good. So also with larger data sets, it's really hard to put everything in order of large data sets. It's also hard to add up all observations of large data sets. So we do rely a little bit on our calculator. That's in your next video. I'll show you how to do the mean and the median on your calculator. Okay, but getting back to this, so that's in the next video. We're going to be talking about resistance. So let's look at this definition. A numerical summary of data is said to be resistant if extreme values, either large or small, relative to the data, do not affect its value substantially. So let's kind of go about this intuitively. Let's go back up to our example. So let's say in this data set that we have here, this largest value, right, was 49.26. Let's say something happened, maybe a data entry error, and instead of 49.26, we have an extreme value relative to the data set, like $100. What's going to be affected? Is the median going to be affected? Not at all. The median would have no effect on the median because we're looking at the physical middle, and that extreme value is just going to stay at the extremes. It's not going to affect the physical middle. Will it affect the mean? Yes, because we're going to be adding that $100 to the rest of the values. It's going to throw the mean off. So we have this little snippet right here. Which one is resistant to extreme values? Which one is not affected by extreme values? The median. The median is resistant. It is not affected by extreme values. And the mean is not resistant to those extreme values. All right, it is affected by extreme values. And when we add 100 instead of 50, that's going to mess up our mean. Okay, so because the median is not affected by extreme values, we have this little snippet here. Use the median to measure central tendency if the data has extreme values. So it's not affected because the median is resistant. All right, so what do extreme values sometimes look like in a graph? That's what that skewed right and skewed left are. Most of the majority is in that tall part of the graph. But those tails represent extreme values. So if we have skewed right or skewed left, that's a better measure of central tendency. All right, so before we look at mode, I'm going to look at a few different distributions just at that point of resistance. So I'm going to draw 3 curves. One is going to be bell-shaped. One is going to be skewed right. The other one will be skewed left. All right, so we have these 3 things. Okay, so in bell-shaped, remember our mean is right down the middle. All right, so that's your mu. With skewed right, we already talked about it. These extreme values are going to pull the mean towards the tail. So maybe the mean is going to be somewhere right there. And likewise, in skewed left, the extreme values are over here. It's going to pull the mean towards those extreme values because the mean is not resistant. All right, and now let's consider the median, the physical middle. All right, bell-shaped symmetric, they're the same. Skewed right, the median is going to be hanging out with the majority of the data, and that's where the height is. Height is frequency. So maybe our mean will be somewhere right here. So for skewed right, the median is with the majority of the data, it's less than mu. And then finally skewed left, remember height is frequency. So height is where most of the data is. So maybe our mean is somewhere right there. So in skewed left, the mean is less than the median. All right, so remember the tails represent those extreme values. And this illustrates that the median hangs out where most of the data is. That's what we want. Central tendency should measure kind of the average of our data. Okay, our last measure of central tendency is the mode. And it's the most frequent observation of the variable that occurs in the data set. So we have lots of possibilities. We can have several modes. We can have 0 modes, 3 modes, 2 modes. It depends, right? So let's look at this example. We have our flight time. We're not going to do the mean and median for this repeat example. We're going to just do the mode. So we would have to go through and we would have to find values that occur most frequently. So let's see. I see two 60s. Anything else repeat? No. All right, so I guess it just has one mode. So the mode is just that value that repeats. Central tendencies have units, so it's not 200, whoops. It's not 260, sorry about that, it's 260 minutes. Okay, and then we have this final example for this problem, I should say. They said, suppose 267, where is that? Is incorrectly recorded as 627, so a little bit of a data entry error. How does this affect the mean? It would make it bigger, right? And then what about the median? Well, remember, we're just looking at the physical middle. And that extreme value is in the tails. It's on the outside. So the median, I'll write it in a different color, is not affected. And what property of the median does this illustrate? The median is resistant. And it's helpful to say in your head, resistant to extreme values. All right. Final example is an application, and one that reminds us not to rely too heavily on our calculator. So we have that Mr. Zorro finds the mean height of all 14 students in his statistics class to be 68 inches. Just as Mr. Zorro finishes explaining how to get the mean, Danielle walks in late. Danielle is 65 inches tall. What is the new mean height of the 15 students in class? Okay, so I like to write down my information. So I'm just going to start writing some tidbits from this problem. So first of all, the mean height of 14 students is 68 inches. Danielle walks in late. She's the 15th member, so I'm just going to use this notation. She's the 15th observation. She's 65 inches. We'll worry about units at the end. Here's the problem. What is the mean height? So x bar sub 15. All right, so there you go. Let's write down other things we know. I know that if I wanted to find x bar with the 15 students, I would have to take the sum of the 15 all the students' heights, and I would divide it by 15. All right, likewise, what else do I know? I know Mr. Zuro found the average height of all 14 students by adding up all 14 heights and then dividing by 14. Okay, and we know that Danielle walked in late. So what did he really have to do with this calculation? Well, he added this up before Danielle got there. And then how did he get from the sum of 14 heights to the sum of 15? He had to add Danielle's height in. So he had to add 65 to get the sum of all 15. Okay, so this is going to kind of run our strategy. If we can figure out the sum of the 14 heights, then all we have to do is add 65 and divide by 15. Then we have our new average. So this is what we're going to do. We actually know what the sum of 14 heights divided by 14 is. We know that mean. They told us that it's 68. So we can think of this as an algebra problem where this whole numerator is unknown. So how could we solve for that numerator? Multiply both sides by 14. Clear the denominators, right? So now the sum of the heights is 68 times 14. And that's nice too, because that kind of tells us what the central tendency is. We're kind of assuming all 14 students have the height of 68. Okay, so we're almost done. Remember why we wanted to get that? It's always important to remember our why. We're trying to find the mean of 15. So Mr. Zuro, again, after Danielle came in, he did the sum of the 14 heights that he already calculated, added her height, which was 65, and then now divided by 15. So we're almost done. We just found the sum of 14 heights to be this. We're going to add her height in and divide by the now 15 students. Let's put that in our calculator. Order of operations. Maybe you need to put your numerator in parentheses for that. But we get 67.8. What's full credit? What are the units? Good. Inches. And that's that.